I'm Stephen Pullen, and today I'll be talking about Sally Floyd, a pioneer in the active queue management field. First, I want to start with Sally Floyd's early life. She was born on May 20th to Edwin and Margaret Floyd. Her father was a mathematician, and her mother was a nurse. She started her college education at the University of Michigan, which she attended for 1 year. She then transferred to the University of California, Berkeley, where she graduated at 21 with a bachelor's degree in sociology and a minor in mathematics. To find a better way to support herself, Floyd went back to school, this time at Merritt Community College, to obtain an electronics education. This led to her finding a job as a computer systems engineer at Bay Area Rapid Transit. It was in this position that Floyd realized she had a passion for theoretical computer science, which caused her to once again return to school, this time going back again to the University of California. It was here that Floyd finished her schooling for good, earning a PhD in computational learning theory. Sally Floyd was most known for her work on internet congestion control. Her most noteworthy contribution being her invention of random early detection alongside Van Jacobson. She also created explicit congestion notification, which, along with RED, I will go into more depth on shortly. It was these works that helped Sally Floyd to create the field of active queue management, once again alongside Van Jacobson. Her work was a great asset to many in the field of computer science, as her most popular paper on RED was cited 9,000 times, with 50,000 further citations coming from her other works. This led her to be one of the top 10 most cited CS researchers in 2007, which is another testament to the importance of her work. Random early detection, or RED, is an algorithm created in the 1990s by Sally Floyd to reduce congestion in queues. The RED algorithm reduces the drop rate of packets by purposely dropping packets as the queue fills and the probability of an accidental drop increases. This practice is the basis for the active queue management field, and RED is a large reason why Sally Floyd is accredited with the creation of this field. The RED algorithm makes decisions based on three main values: minimum queue length threshold, maximum queue length threshold, and average queue length. When average queue length is less than the minimum threshold, all packets are accepted, as is shown in the first third of the first figure. As the queue gets busier, average queue length will pass the minimum threshold and begin to approach the maximum threshold. This is the middle section of Figure 1. Based on how close the average queue time is to the maximum threshold and the likelihood of the packet being considered accidentally dropping, the probability of the RED algorithm randomly selecting that packet to be dropped increases, which is demonstrated by the increasing slope. Once the average queue time reaches the maximum threshold, no more packets will be added to the queue, and all incoming packets will be dropped. A visual representation of this is shown in Figure 2, where packets joining the line after the max threshold has been met are instantly dropped off without any calculation. Additionally, since the odds of a packet being purposefully dropped is dependent on both the average length of the queue as well as the likelihood of accidental dropping, this means that those attempting to send large amounts of data will have a higher chance of their packet dropping. This piece of the algorithm ensures that RED is fair to all attempting to join the queue. The efficiency and equality that RED algorithm provides has stood the test of time, and while the exact variant of RED that Sally Floyd created may no longer be commonly used, many variations of her base algorithm are seen widely in the field of active queue management. Sally Floyd recognized that a weakness in her RED algorithm was a lack of explicit communication with the sender after a purposely dropped packet. To remedy this, Sally created the optional explicit congestion notification feature. ECN allows the receiver of information to label purposefully dropped packets as dropped due to congestion. These packets would be sent back to the sender of the data, allowing it to reduce the traffic if possible, to both decrease the congestion and increase the likelihood of a packet being successfully sent. The ECN system was largely beneficial, as the amount of packet loss, latency, and jitter were reduced between two ECN-equipped endpoints. Sally Floyd also improved the system in which routers communicate with each other by adding jitter to their messages. For a router to send information to a network, It will send a message to connected routers asking for the route to that network. Those routers will respond with their routing table, which contains the known paths to the requested network. This process is repeated every 30 seconds, beginning at the time each router is powered on. The process of supplying routing tables is most effective if many routers are asking for and supplying routes at varied time points in a 30-second cycle. Due to the varied initialization time of individual routers, it was assumed that routes would be sent near perpetually. However, Sally Floyd, along with von Jacobson, showed that routers would eventually synchronize after an extended period. This led to the now common practice of adding small random delays to these 30-second timers to avoid an eventual synchronization.